Hello and welcome back. Today we'll continue looking at trigonometric functions, and for this first problem, let's complete a warm-up. So pause the video, try this on your own, and come back. All right, so now that you're back and you've paused it, let's go over this just to review. So we consider this is the sine function, but we definitely see there's transformations in here. And the first thing we can see is the -4. That's going to have an impact on the amplitude and a reflection. There's no vertical shift, so that could be y equals 0. When we look inside the factor, well, we can see that the b equals 2/3. So when the b is 2/3, that's going to change the period. And remember, the period is usually 2 pi. So when we divide 2 pi by 2/3, we'll get 3 pi. And then if we consider the distance between those critical points, it'll just be 3 pi over 4. Now we definitely also see a c value, and we have to be careful because there is going to be a horizontal translation, but remember it's going to be c over b. So another way you can solve it or figure out where it starts and ends is to set the factor equal to 0 for the start and set the factor equal to 2 pi where it usually ends. And when we solve it, we get x equals pi over 2, and then x equals 7 pi over 2. And that makes sense because we said that the period was 3 pi. So when I label and identify the x values, the angles, the key points that we're looking at, I'm going to start with pi over 2. I'll end with 7 pi over 2. And I'm going to add 3 pi over 4 each time. So this is really 2 pi over 4. So adding 3 pi over 4 makes 5 pi over 4. Then we get 8 pi over 4, which is really 2 pi. And then we get 11 pi over 4. And then we get back to 7 pi or 14 pi over 4. Now the regular sine function, the parent sine, and I did include this transformations or this horizontal translation and change in period. So I could put that, or you could just put theta, just for your notes and your reference. So we're starting with 0 for sine, remember, going up to 1, back to 0, down to -1, and then back up to 0. That's the parent function for sine. Now I want to make sure I also include the change with the amplitude. So it's going to be -4 times whatever y value I had before. So I'm just going to multiply everything by -4, just the y values. So when we consider how to plot this, our key points are going to be pi over 2, 0, 5 pi over 4, -4, 2 pi, 0, 11 pi over 4, 4, and 7 pi over 2, 0. All right, so when we graph that, so we'll start with pi over 2 here, so that's 0. And then 5 pi over 4 would be about here, halfway between here. So this would be -4. Then at 2 pi, it's back to 0. And then at 11 pi over 4, it should be about here. It's up to 4 and then back to 0. So we can see one period completed there. Now let's consider the tangent function. So you probably remember the tangent function as a quotient identity, sine over x. So to evaluate these values for theta, we can also reference the unit circle down here and divide the y value by the x value. So at -pi over 2, we have -1 over 0, which is undefined. Remember, we cannot divide by 0. So that's going to indicate one of the asymptotes. At -pi over 3, which is also 5 pi over 3 in the fourth quadrant, we're going to have -√3 over 2 divided by 1/2. So that will just be -√3. At -pi over 4, well, that's also 45, 45, 90 triangle, but we know that we're going to have the same values for x and y, just one will be negative, so that's -1. At -pi over 6, we're going to have -1/2 divided by √3 over 2, 1 over -√3. Well, we could just rewrite that as -√3 over 3. Now at 0, we're going to have a y value of 0 and an x value of 1. So that'll just equal 0. And then when we look at the other angles in the first quadrant, they're going to look identical to the ones in the fourth quadrant, but now they're going to be positive. So we're going to have root 3 over 3, positive 1, positive root 3, and then undefined. Because, well, again, we're going to have positive 1 divided by 0 here. So we could use a unit circle, or we could use special triangles to find those values. So what's important is that when we start to graph it, we're going to notice that the domain covers all these values except for those that are undefined. And those will be our vertical asymptotes. So remember, tangent is going to be undefined whenever cosine equals 0, because cosine is in the denominator. And if you notice, we have an asymptote at pi over 2, and the distance between all those asymptotes will be pi. So the equation, the general equation for vertical asymptotes for tangent is x equals pi over 2 plus n times pi. And that would also help us find the restriction on the domain. Well, the range is going to be all real numbers. So when we graph it, we can see them below. Also on the graph, you can notice that the zeros for tangent are when sine equals 0. And they occur at every pi. So here we have the values, and these were the asymptotes that we figured out. We can see that as x approaches negative pi over 2, and I'm just going to write here, we know that the function is approaching negative infinity. And as x approaches positive pi over 2, y approaches positive infinity. So we have an increasing function. And we have the period of the tangent function is just going to be pi. It continues that cycle over and over. We can also tell graphically in looking at this that it's symmetric about the origin. So whenever we're trying to figure out the vertical asymptotes for the tangent, we need to make sure we find that factor and set them equal to the normal asymptotes, negative pi over 2 and pi over 2. Now let's consider this sketch. All right, we'll look at tangent of x over 4. Now remember, we said that the period for tangent is pi. So now we're going to divide pi by b. So we're dividing it by 1/4, which is really going to be 4 pi. So it's going to complete that whole cycle in 4 pi. So if we wanted to figure out where it's going to start, well, we set x over 4 equal to negative pi over 2. And so when we multiply this out, we'll multiply by 4, we get x equals, and that'll just be negative 2 pi. And then if we wanted to figure out where it's going to end, well, you could probably notice it pretty easily. But we'll set this equation equal to the asymptote pi over 2. And again, here we get x equals 2 pi. And again, the distance between those two asymptotes is 4 pi. Now the zeros are always halfway in between. So we could say, well, the zeros are going to occur at 0 plus 4 pi, because every time we have a new period, it's going to be happening again. So 4 pi n. And then for the vertical asymptotes, well, we know they're going to occur at 2 pi plus 4 pi n, because each of those asymptotes will have 4 pi of that whole cycle in between. So if we're going to sketch this graph, I'm just going to easily just leave this as pi. Might be easier So what I want to do is make sure I label the graph here, and I'm just going to label just, a couple cycles here. So we know that we're going to have an asymptote at -2 pi, at 2 pi, the origin 0, 0 is going to be an intercept, or 0, and we know it's going to be increasing as it approaches 2 pi and decreasing as it approaches -2 pi. And if we want to keep going, well, let me just include up to 6 pi so we could have more cycles here. So I'm going to label these asymptotes again. Remember the distance is 4 pi. And then halfway in between are going to be those zeros or intercepts. And then just continues that cycle. Now let's look at the next problem. So for this one, we know that there is definitely going to be a horizontal translation. You can see that C right here. And that's going to move everything to the right, pi over 4. Now the value for B is still 1. So that means the period is just still going to be pi. So if we wanted to figure out exactly where it's going to start, well, it's not too tricky because remember, it usually starts at pi over 2. So what we can do is say, well, let's set x minus pi over 4 equal to -pi over 2 for the start, and x minus pi over 4 equal to positive pi over 2. So remember, everything is getting shifted to the right, pi over 4. So that would make sense that x, that first asymptote, would be -pi over 4. And then the ending part would be 3 pi over 4 because that also shifted to the right, pi over 4. Now remember, the midpoint between those two asymptotes, I shouldn't say, well, it is technically midpoint, but the halfway point between the two asymptotes is the 0. So usually the 0 is at 0, and everything shifted over to the right, pi over 4. So if you wanted to double check, you can also add pi over 2 to the first asymptote, and you'll get pi over 4. And then we know that it's going to repeat, so that's going to be plus pi n. We know that the asymptotes are also going to repeat every pi n, so we could say 3 pi over 4 plus pi n. All right, so whenever we're graphing it, we can determine whatever we want on our axes. So since we have a lot of pi over 4s, I'll put pi over 4. This is pi over 2. All right, so for the first one here, I'm going to label the asymptotes at -pi over 4 and 3 pi over 4. And we can clearly see that halfway in between, there's a different color here, is the 0 or the intercept. And there's no other transformation, so it's going to be an increasing function. And we know that this is going to continue every pi. So we can keep going with all of these asymptotes. And again, that intercept is halfway in between the two asymptotes. So if you remember, the cotangent function is also a quotient function, and it can be written as cosine over sine. So when we consider these values, we're actually going to look at the x divided by the y. So at 0, the x is 1 and the y is 0. But remember, we can't divide by 0, so that's going to be undefined. At pi over 6, we're going to have root 3 over 2 divided by 1/2, so that's just root 3. At pi over 4, we'll have root 2 over 2 divided by root 2 over 2, it's 45. So we know that'll be 1. At pi over 3, we'll have 1/2 divided by root 3 over 2, which can be simplified and rationalized into root 3 over 3. At pi over 2, well, the x is 0, the y is 1, so that's just 0. Now looking at the second quadrant, remember all of these are going to be the same, except now we're changing signs. So anything with sine will be negative. So all of these terms will be negative. So this is negative root 3 over 3. 3 pi over 4 is negative 1. 5 pi over 6 is negative root 3. And at pi, we're going to have negative 1 over 0, which is undefined. So it's important to consider where the values are undefined, because that tells us where we're going to have vertical asymptotes. So cotangent is undefined wherever sine equals 0. So we're going to have vertical asymptotes at pi and anything with pi n. So 2 pi, 0, 3 pi, okay? The zeros, on the other hand, are going to be when cosine equals 0. And if you notice, that's going to be at pi over 2, and the period for cotangent is pi, so it's plus pi n. Now when we look at the function, it looks very, very similar to the tangent, but you can see that it is a decreasing function. It's the reflection on the x-axis. So we're going to have the same sort of symmetry. It's about the origin. We're going to also have the same range. This is all real numbers, but we're going to have a restriction on the domain because it also has vertical asymptotes. And again, when you're trying to find the vertical asymptotes, you want to set it to the values that usually are asymptotes, 0 and pi. Now for this problem, we're going to use a graph to solve the equation cotangent of x equals root 3. Now remember, we had said that the period is pi, and we also said that the asymptotes were at 0 and pi. So I'm just going to label this. So we have pi over 4, pi over 2, 3 pi over 4, and pi. And essentially I'm just going to have 3 pi over, just pi over 2 each time. So here we have 3 pi over 2, and then 2 pi. So we're looking between the interval negative 2 pi, so I'll have negative 2 pi over here, to 2 pi. So let me just label these here. And we'll put this is pi, and we'll put this is pi over 2. And these are all negative. Okay, and essentially each of those spaces is a pi over 4. Now, looking at root 3, we know that root 3 is about, it's going to definitely less than 2, about 1.7. But when we usually solved it, we would always say, which quadrant is it in? Well, if it's root 3, we could say it's in the first quadrant. We would draw the triangle and label the sides. So for this one, we're going to label the graph or identify parts of the graph. Here's one of the asymptotes. And then we have another asymptote at pi, another asymptote at 2 pi. So at every pi. And we know that here, in between, halfway in between, will be the function's 0. And the cotangent is decreasing. So if I was going to sketch that line about, definitely a little less than 2, so about 1.7, say it's about here, would be my y equals root 3. Well, you can see right away there's definitely going to be 4 times when it equals root 3. And even though it sometimes looks like it's on my pi over 4, it's not always there. So we have to figure out what that angle is, and we can go back to the triangle. So we know that cotangent is root 3, the adjacent over the opposite, and we know that the opposite angle in the 30, 60, 90 of 1 would be the 30, or pi over 6. So this first point must be, I'll use a different color here. This must be pi over 6 root 3. If we're going to find all the other values, all we have to do is add or subtract pi, because the period is pi. So we have pi over 6 as a solution. I'm just going to put x equals here. And to find the one over here, we just add pi, which is really 6 pi over 6, so that's 7 pi over 6. And then for this one over here, we'd have to subtract pi, so we'll have negative 5 pi over 6. And then for the last one, again, subtract 6 pi, negative 11 pi over 6. And we can see that there's going to be 4 places, 4 intersections, 4 solutions when the cotangent of the graph equals root 3. Now let's look at this next one. So this one is a cotangent of 2x. You can see right away that it's going to affect the period. The period is usually pi, but now we divide it by 2, the b. So it's going to be cut in half. If we want to figure out where it's going to start and end, we could always set it equal to 0 and then set it equal to pi, because those are the usual asymptotes for cotangent. Well, you can see right away, not too difficult of math, but you can see it's going to be 0 and pi over 2. So the vertical asymptotes are going to be pi over 2 and then plus pi over 2 plus pi over 2. So I could just write this as pi over 2n. And then if we look at the zeros, let me just graph these here. I'll put pi over 2 here. And I'll put negative pi over 2 here. Actually, I'm going to make it look even more narrow because it does look. Let's leave this as a regular pi over 2. This is negative pi and pi. All right, so we can see these asymptotes are going to occur at all the pi over 2's plus pi over 2. And then the cotangent function is still decreasing, and the halfway point, which is pi over 4, and if you add plus pi over 2, n, I'm going to rewrite that so it doesn't look like it's in the denominator. So pi over 4 plus pi over 2, or pi n over 2, might be better. We can see that those intercepts will be halfway in between. And we can sketch the graph. So cotangent is decreasing. Looks almost like a cubic. And it's going to go towards positive infinity or to negative infinity, depending on the asymptote. Now let's look at the graphs of cosecant and secant. So just as a refresher, remember cosecant is the reciprocal of sine. And so the secant is the reciprocal of cosine. So they're going to be actually very similar. Whenever we look at cosecant, we have to take into consideration sine. So it's really important to sketch sine so that we can see cosecant. So after you sketch sine, wherever we have the intercepts, wherever the function equals 0, we're going to have vertical asymptotes. So you can see that the domain is going to be all real numbers except for the asymptotes, which are pi n. And here you can see on the graph an asymptote at pi, another asymptote at 2 pi, another asymptote at 0, another asymptote at negative pi. Cosecant completes a full cycle. It almost looks like a parabola opening up and a parabola opening down. It completes a full period in 2 pi. If we look at the range of the graph, remember we do have the sine graph here, so it's a little misleading. But looking at the graph only stays in these positive values and only goes to negative or to positive 1, and then has this gap where sine is, and then it'll be from negative infinity to negative 1. The function is also symmetrical about the origin. So whenever we're looking at the vertical asymptotes, make sure you're determining where sine of x equals 0. It's the zeros of the sine, because again, the sine function is its reciprocal, so we can't divide by 0. The max and min values will always be halfway in between those asymptotes. And so we have those asymptotes separated by pi, and halfway in between pi is pi over 2. So you can always see a max or a min at pi over 2 plus pi n. Now, as we look at secant, make sure you find the differences. So there's definitely a lot of similarities. We still have the same period. We still have the same range. But if you notice, the asymptotes are going to be at pi over 2 plus pi n, because that is when cosine equals 0. So if you're going to find the vertical asymptotes, it'll be at pi over 2 plus pi. So 3 pi over 2, negative pi over 2, and then if you want to find those max and min values, that's when we'll have it at n times pi. All right. Again, when graphing the cosecant or the secant, you want to make sure that you're graphing the reciprocal function first, so either sine or cosine. It does help to use a lighter color or a dashed line. Then you want to sketch the vertical asymptotes. Make sure you draw those boundaries. And the vertical asymptotes, remember, they're going to intersect at the midline, or when sine and cosine equal 0. Then sketch the cosecant and the secant using max and min values, almost like parabolas. All right, let's look at this problem. So here we have cosecant. So we're going to start by graphing sine. So sine of x, let me see if I can find a lighter color. Oh, it is gray here. Okay, so whenever we graph the sine function, I'll use gray. Remember, the period is still the same. It's still 2 pi divided by b, and our b is 1. So this will be 2 pi. The distance between those critical points, or key points, would be the quarters. So 2 pi divided by 4 is just pi over 2. If we're going to figure out where this is going to start and end, well, you can see really quickly there's going to be a shift. We can see that that's going to be shifted to the left, pi over 2. So we could say this is going to start at negative pi over 2. And we usually end at 2 pi, so it's going to be 2 pi plus pi over 2. So we can write that as 4 pi over 2. So it'll be subtracting, that's since it's going to the left, that's going to be 3 pi over 2. All right, so now we have definitely a period of 2 pi. All right, so let's label these values here. So the first part is the first starting point for our angle, negative pi over 2. We're going to end with 3 pi over 2. So when we add pi over 2, we get 0, pi over 2, then 2 pi over 2, which is just pi, and then 3 pi over 2. Now let's look at the amplitude. The amplitude here is 2. So that means we're going to have to make sure we're going to multiply that function by 2. There is no change in the midline. There's no vertical shift. All right, so let's go back to sine function. So we know the original sine function, just the parent, starts at 0, goes to 1, back to 0, down to -1, and then back to 0. Well, if we're going to multiply this by 2, an amplitude, we know that this is going to be 0, 2, 0, -2, 0. All right, so let's sketch this graph. And I'm going to label all these points here, just the first few here. This is going to be in increments of pi over 2. So this is pi over 2. This is pi, 3 pi over 2. We can just say 2 pi. And you can keep going here, 3 pi, there's 4 pi. Negative pi here, negative 2 pi, negative 3 pi, and negative 4 pi. So remember, we're going to graph this sine first. And I'm going to use gray to graph the sine, but I know that also this has an amplitude of 2. So I just want to make sure I'm going to go by just regular units here just to show that. All right, so first let's graph the sine. So sine was at negative pi over 2, it's 0. At 0, it's going to be 2. Then at pi over 2, it's 0. At pi, it's -2. And then 3 pi over 2. So you can kind of see that this graph, you can just keep going since we evenly spaced everything. And this is the sine curve. And I'm using a lighter color. You can use dashed lines as well. But remember, that's going to help us graph the cosecant. So remember, the cosecant is going to have asymptotes, and I'll use red, I'll use a bright color. It's going to have asymptotes when sine equals 0. So every time we have these zeros, that line was a little off, we're going to have a vertical asymptote. So you can see that there are going to be a lot of vertical asymptotes here between -4 pi and 4 pi. All right, and now let's sketch the graph, because really the asymptotes are for the graph, but it's really not the function, right? So let's graph it in blue, and we can see that this cosecant has minimum values, relative mins, relative maximums. And if you notice, the relative maximum for sine becomes the relative minimum for cosecant. So let's identify these relative max and mins. So again, the relative max here, well, that's at pi. So we're going to have a value at pi, and then remember the period for this function was 2 pi. And so we're going to add 2 pi n here. The relative min, there's one here at the y-intercept, and the next one is at 2 pi. So again, these are spaced out by 2 pi n, which is the period. The vertical asymptotes are a little bit closer, and we can notice that the first one here is pi over 2, and they're all going to be separated by only a distance of pi n. Now for graphing secant of pi x, we're going to have the same process. Remember, we're going to start by graphing the reciprocal function, which is cosine. And let me just be specific because we're trying to graph cosine of pi x. So I'm going to come back to the secant. Let's graph cosine of pi x. So remember the cosine of pi x, well, the period is usually 2 pi. If we divide it by b, we know the period is 2. We know that the distance between those critical points, or those key points, is by quarters. So 2 over 4 is just 1/2. Now I'm graphing cosine the same way that I usually do. I start with usually 0. So we know that this is just going to still be 0 because pi times x equals 0. X will still equal 0. And then pi times x, if we say, well, that equals 2 pi, where it usually ends, well, you know that period was 2, so it just ended at 2. This does not have an amplitude or vertical, it has an amplitude of 1, but no vertical stretch. And we could say the midline is still y equals 0 for the cosine. So graphing the cosine, again, we're going to start with 0. We're going to add 1/2 every time. So this is just 3/2, and then 2. And we know cosine of just regular, good old cosine starts at 1, goes to 0, -1, then 0, then back to 1. Now we know that we're going to have to change this into secant. All right, so we have these values for cosine of pi of x. So let me just label this here. So I'll just label these 1, 2, 4. And I'm just going to sketch the graph here. These are just going by, well, I made them go by halves, didn't I? So I guess I'll just make these go by halves as well. Okay, so that's -2, not -3. All right, so graphing this, I'm just going to graph this in a lighter color. Okay, but we have the cosine at 0 equals 1. At 1/2, it equals 0. At 1, it's -1. And then you can see kind of this cosine curve here. And what I'm going to do is just trace this and just sketch the cosine curve in this light gray color. Oh, does not look perfect, but very close. And we're going to use this graph to graph the secant. So anytime we have a 0, or when cosine equals 0, that's going to be an asymptote. So lots of asymptotes here. And then whenever we have a maximum for the cosine, it will become a relative minimum for secant, and any minimum, I'm going to use a different color here, any minimum for cosine becomes a relative maximum for secant. So you can see these parabolas here, a lot of colors, but remember here I have the gray is our cosine, the pink is our asymptotes, and then the blue shows our cosecant. So again, just refreshing on the values for secant. We notice that the secant is going to have a relative maximum at 1 and then 3. So it's going to be 1 plus, and the period, remember, was 2. So 2n. And then it's going to have a relative minimum here at 0. And then again at 2. It's a little off over there. But the period was 2, so it's 2n. And then the vertical asymptotes were at the halfway point. So it's going to be at 1/2 plus, and you can notice right here, it's just going to be 1 unit in between. So it's just going to be n for those vertical asymptotes. The last thing we want to go over are the damped trigonometric functions. And I say damped. So the factor that we're dampening the function is always going to be the product or multiplied with the trig function. So here we have f of x equals x times sine of x. We know that sine of x has to stay between -1 and 1. But if we multiply this by x, well, now it shows that x times sine of x has to stay between -x and x. So essentially we have these two boundaries. There's negative x and there's y equals x. You can notice that sine will still equal 0 at pi n. And then you can notice that it's going to have it's going to have a relative max or min at pi over 2, just like the regular sine would, plus pi n. Now looking at this one has a dampening factor of e to the negative x. That should be negative. And so for here we have, well, e to the negative x, if we multiply that by sine of x, well, we know that this is going to have to stay between, let me use a different color, e to the negative x and negative e to the negative x. And you can see the sine function still staying between these values. And still here at 0, 0, you can notice that it still has that x-intercept. And the 3 in this problem, the sine of 3x, is going to change the period. So remember, it's normally 2 pi, so this period will be now 2 pi over 3. So that's going to change where we have these zeros and where it touches the function. Okay, but it's very similar to what we covered with just regular sine and cosine, but now you have a dampening factor. So looking at that boundary, and those boundaries are reflections on the x-axis. So before we go, just make sure you review the trig functions, and I'll see you all in class.